Hello, this process and presentation is about our research into leader election security in federated learning. The goals of this research was to understand security risks in leader election for decentralized federated learning, compare decentralized federated learning and centralized federated learning under adversarial control, investigate layer-specific attacks on Wave2Vec, which is an acoustic speech recognition model which basically converts audio to text, very much like subtitles would do on a YouTube video. It automatically does this, and we wanted to investigate how the model could be degraded on performance and security on the training and learning processes of this model. And finally, we evaluate leader election policies under attack, which is rotating versus non-rotating. And I can hear you asking, what is federated learning? Federated learning is a process which is meant to be secure and stable and private and ensure everything you'd want to be ensured while training AI models. However, there is a single point of failure in federated learning, which is the centralized server. So how federated learning works is you have a section of clients who gather weights and information, and they all transmit this to one centralized server who aggregates the model's weights, and this repeats over rounds, and eventually the model will converge and come to a stable point, and that model would be trained. However, if the centralized server is compromised, this training process falls apart, as the single point of failure needs to be honest and reliable. So to combat this, a process called decentralized federated learning was introduced, and this, instead of using a centralized server, elects leaders. So leaders are elected to be the central server each round, and the policies are either rotating or non-rotating, and they came from previous consensus algorithms, or some was designed for federated learning and decentralized federated learning specifically. However, we today prove that the difference between rotating and non-rotating policies, and how the leader is still a single point of failure at the current time that he is elected the leader. But the research didn't start with federated learning. The research started on attacking ASR models, specifically Wave2Vec and Huber. So to show this, we've got a poster, which I'll switch to now. So this project actually started as research into defense against nefarious artificial intelligence usage, and the aim was to generate a PGD-based defense on the acoustic speech recognition systems to prevent cyber criminals using these newly emerging AI tools to solve specifically audio captures automatically, which should in turn deny scalable online account creation. So if you've ever had bots message on Facebook, which are fake accounts trying to scam you, deceive you, and make money from you, or impersonate somebody, or celebrities message, we propose a solution of adding audio captures, very much like image captures, that are attacked with a projected gradient descent attack, and this should stop models being used to automatically complete audio captures. So we propose a projected gradient descent based defense. This works through taking a clean audio sample, computing the gradient loss, then applying small, carefully crafted perturbations to the audio in the same direction as the gradient, as the loss function's gradient. This would in turn attack in such a way where models aren't able to then transcribe the audio. However, a legit human would be able to transcribe the audio. And I'm sure you're wondering how this is related to federated learning and leader election security. But by completing this project, we analysed baseline performance rates of Wave2Vec, which is used in the next project. Well, it's the same project, it just carries over. And this showed that these models are vulnerable, and as we can see on the graph on the left-hand side, even with adding different noise types, so the top left graph, even by adding different noise types, these models have a very, very high word error rate. And this error rate is used to determine a model's functionality and how good it is at transcribing. And we can see that as less noise gets added, different dBs of noise, SNR levels, which is your signal noise ratio levels, and 20 means that there's less noise, and -5 is more noise. So 0 is a flat line of even audio and background noise. And we can see the word error rate and the model's performance downgrading as we go to the left. So it starts off awfully at -5 and slowly gets better, but the model still makes mistakes. And we can see in the bottom right, which is the Wave2Vec model, that on audio captures, once attacked with this PGD attack, they have a 100% failure rate. So that means there is no exact match that is possible once attacked. And Wave2Vec has a 99% word error rate and an 81.6 word error rate on samples. That's the difference between a data set found online on Kaggle and audio captures generated using Google text-to-speech, which is a combination of letters and numbers. And we can still see that 100% human pass rate on the adversarial captures and 80% on the slightly less accurate Kaggle dataset. And this led us to know that there's limitations and there's a problem with these models in general, and they're growing more and more useful in day-to-day life. So we then switched to the research being in federated learning and adversarial training to see how. So the contributions we provide in this research specific to federated learning are we can show a compromised leader versus a compromised server, and we can show that a compromised leader, which is elected in decentralized federated learning, has the same degradation effect on performance as a compromised central server. We can show layer-specific vulnerabilities. We can target different layers of an acoustic speech recognition model and provide different effects on the word error rate, although all these word error rates are still very, very high. We can also show a frozen layer attack. We can show that with a single adversarial client, if the adversary can manipulate otherwise frozen layers, it leads the model to an unrecoverable collapse, as each round the global model is pushed away from the correct state, which this will be explained further as we get into the results, and I'm sure you'll come to understand how that works. Additionally, we can prove that a compromised or adversarial clients have no meaningful impact on a global model. Over simulated rounds of training in a decentralized federated learning environment, having a percentage of clients push adversarial updates into training fails to bypass a federated averaging method, and the global model still trains to a lower word error rate. Finally, we compare rotating versus non-rotating leader election methods. We implement 9 leader election methods, some rotating and some static, proving that a rotating leader election policy allows for honest clients to recover the model state, whereas a static leader election policy doesn't allow for recovery. So this is the CFL compromised server, CFL being centralized federated learning, which again is where the server is a single point of failure. Previous research has shown that this is a single point of failure and acknowledged it, which is why the decentralized approach was introduced. However, we then needed to find this ourselves and prove this to continue research. So by attacking the model, we can show that in a compromised server, we invert gradients and we push them 10% in the wrong direction in a different test. we achieve 100% word error rate and 74% word error rate, compared to the baseline 19% of the model. We do this by, before returning to the client, attacking the gradients and the weights and pushing them away from where they're meant to be. If they're meant to be at point A, they're at point minus A, or they're at point A plus or minus 10% away from the direction they're meant to be averaging in. So we can see again the word error rate spikes to 100% for the full inversion and to 74% at even just 10% inversion. And the baseline model transcribes at 19.3%. So we prove that with a compromised server, there's a massive flaw in centralized federated learning. And to carry on this research, we then prove that the leader in the decentralized federated learning has the same impact as a compromised central server. So this is the decentralized approach and the results. So we simulated a toy decentralized federated learning setup, which was run locally. And again, we used the Wave 2 Vec 2.0 model, which is from Facebook. Again, with the baseline model having a 19% word error rate. A compromised leader in decentralized federated learning has the same destructive impact as a compromised central server in CFL, showing that leader election security is critical, and this research holds significant value in this field. Using the same sign flip attack we used previously, a compromised leader can drive the model to 100% word error rate, either by gradually pushing updates, say 10% each round, until the model destabilizes, or by fully inverting weights to render it unusable after a single round. And with a compromised leader, we can see the 100% word error rate is again achieved with a train loss and evaluation loss of 4.1 and 24.9, which is significantly higher than it should be. And the model at this point also is only able to transcribe the letter T, which is interesting to note that the model returns full collapse and full failure. So no matter which audio file you put in, whether that is the quick brown fox or the lazy brown dog, or any audio file would only transcribe the letter T or return blank outputs, which proves that if a leader is compromised in decentralized federated learning, it has the same, if not a worse effect on the model than the centralized approach, in which it is shown that the model, the server, is the single point of failure. So we have proven in our research, in our findings, that it has the same catastrophic effect. This slide is about layer-specific vulnerabilities and how different attacks on different layers can provide different outcomes, or technically the same outcomes. But because of how these models work, they have different layers which do different things, very much like anything really. So the full model attack is every layer, everything's involved, and if we hit it with the same inversion attack, we can see that the word error rate again spikes to 100%, with the train loss being very high and the eval loss being also very high. And this, in our research, didn't allow for any recovery due to attacking the frozen layers, which is spoken about in the next slide. And then following this, we attacked just the classifier head of the model, which again is 100% word error rate, which is interesting to note because attacking this head is a smaller portion of the model, but it just shows how integral the entire model can be, returning 100% word error rate with the same strength attack. And again, the train loss is high and the eval loss is high. And interestingly, if the leader is rotating, this sort of allows for model recovery over a number of rounds, which is interesting and will be discussed further in additional slides. And finally, we have an intermediate layer attack, which again, only attacking these layers returns a 100% word error rate, with a high train loss and a high eval loss, and again can be slightly recovered or fully recovered if the honest clients are strong enough and the leader isn't compromised. So we show that a strong enough attack to any of these layers can cause full model collapse. Not only is the word error rate 100%, the model didn't describe anything at all after these attacks. This occurred for every specific layer attack, with the hypothesis being what the model thinks is said, and the reference being what should be said. So the model should be transcribing, can you remember anything at all, and its hypothesis is blank. Next, we introduce a frozen layer attack where a single client is adversarial, not the leader, and it targets frozen layers which, when fine-tuning a model, certain layers, as I spoke about before, so say the bottom half of the model may be frozen to increase training capacity and speed. So if honest clients can't modify the frozen layers, poisoned updates persist. We've tested 10%, 20%, 40% and 100% sign flip attacks. And we can see in the graph that progressively, as with any sort of 10%, 20% and so on, the model gets worse per round as eventually the model can't recover. The model can never recover, but once the model gets to a certain stage, these attacks just keep slowly poisoning the model each round at the point of aggregation. So it pushes it far enough as these models' layers and weights shouldn't be being changed as they should be frozen. But if an adversary can somehow update these frozen layers in their version of the model without being recognised, then again we can cause model collapse. And the result shows a progressive collapse of the model, small flips, gradual drift, and then large flips lead to rapid failure. And either way, the model still comes out with progressive collapse and total failure. We then investigated adversarial clients, and if 20% of clients were adversarial, guiding weights 20% in the wrong direction, if this would have any meaningful impact on the global model state. The result was the model still trains well and reaches a good global state. After 5 rounds of training with 20% adversarial clients, the word error rate drops to 30%. After more rounds of training, the model still converges in the correct direction, dropping the word error rate. This basically means that even though you've got an adversarial client, the averaging method still pushes, if you're aiming for point A, it still pushes from point B towards point A rather than towards point C. So eventually it will reach point A. It may take longer, but the model still trains well and it will be a usable model. This shows having adversarial clients slows training and model converges, however it doesn't prevent the model training. Finally, we have rotating versus static leader election, and these are the policies and methods in which a leader is elected to be in control of the aggregation of decentralized federated learning. There is static methods and rotating methods. And in the static methods, we can show... So to do this, basically, we compromise 5% each round. 5% of our clients become adversarial. These are randomly selected. And we then change unless the adversary is found to be the leader. And when it is this leader, it will continue attacking. So in static leader election, the results show once compromised, the leader election method fails to recover due to a constant adversarial leader being re-elected each round. As once it's found the leader, the adversary stops rotating and keeps attacking the same leader at the end of each round, shown in the raft-like implementation. In uptime, the adversary was never elected to be the leader, which is just luck of the draw, and it would have the same impact and results as raft. And then in comparison, the rotating leader election methods, which each round the leader rotates, we can see that the top points, so the green, the purple and the blue, you can see the point that the leader was elected and the train loss increasing, and it's slowly decreasing as the rounds progress, meaning that once the leader is then unelected as it's rotated away from the same leader, we have a steady road to recovery where honest clients manage to outweigh the adversary and that update that previously happened, which basically means it's more adaptive and it is recoverable in comparison to the static methods, showing that rotating leader election methods are better implemented. They are more adaptive and in general provide a better layer of security. And the result is rotating leader election methods offer a higher chance of recovery against adversarial leaders. And this is proven just by the graph and how over rounds the model converges back to a stable state. Thank you for listening.